So I just want to take some time to do a quick overview of what we've learned in Chapter 15. And what I'm going to do is a survey of the different models of the atom that we've learned so far, and the key problem with each of those models, and the key experiment that moved us forward to the next model. So if we start with the Dalton model of the atom, it had a couple of key features. The big things were that the atom was indivisible, and atoms of each element are unique. So we have this picture of this single entity, like this might represent a helium atom, this might represent hydrogen. There was no real understanding of what might make each of these things different, but based on chemistry and chemical experiments, Dalton decided that there was probably something unique about each and every atom of each element. Now, the problem with the Dalton model, or better yet, maybe don't think of it as a problem, maybe we want to think of it as an opportunity to improve the model, was the cathode ray tube, this device that could take electrons from one side and accelerate them through a gap. So a real simple picture of that would be something where we have these two electrodes and we apply a real high voltage across these things, and as a result you can take electrons from one side and accelerate them to the other side. So clearly, if your picture of the atom was this thing that was just one single, almost like a billiard ball type particle, once you have evidence that that can be taken apart, you need to improve your model. So that brings us to the Thompson model. A lot of people call this the plum pudding model. It's this model, and here's a picture that can give you an idea or a picture in your brain of what it would be like. You have these electrons that are embedded in positive material. So now the cathode ray tube experiment kind of makes sense, because you can take one of these things and strip it off fairly easily, just like taking the plums out of the pudding. And then the rest of the mass is evenly distributed throughout. And the Thompson model was very good at what it did, but it encountered a problem when it came time, or when somebody performed the alpha particle scattering experiment, Rutherford's experiment. And the problem is that you can't explain alpha particle scattering to the degree at which they scattered if you're thinking of the Thompson model. If you fire alpha particles at something and you're thinking it is like this Thompson plum pudding model, you would predict that the alpha particles should more or less fire straight through, maybe be slightly deflected, but really nothing significant. In reality, the alpha particles were extremely deflected, and sometimes they bounce straight back. And so if you're hanging on to this model of the plum pudding model or the Thompson model, at this point, you have to admit that it doesn't really do a good job of explaining this. In order to explain the alpha particle scattering experiment, we need to, again, redevelop our thinking around this model of the atom. And from what Thompson said, we can extend that. Only Rutherford just suggested that now we have electrons firing around the outside with this really massive, I'll do it in a different color here, real massive positive and protons and neutrons making up the nucleus, making this really massive central spot. And so, yeah, the key features, we have a nucleus with almost all the mass, and the electrons are orbiting. And, again, we picture this solar system model, this model where planets are going around the sun. And so it kind of works nicely. It explains alpha particle scattering. It still has the electrons, really easy to remove on the outside of the atom. Kind of all the chemistry and all the physics of the day could be explained using the Rutherford model. And we'd hold on to it to this day if there wasn't some problems with it. So the problems with the Rutherford model, well, there's two. One is accelerating charges, according to Maxwell's equations with electromagnetic radiation, should emit electromagnetic radiation. So if you have an electron orbiting, it is constantly accelerating. It should be constantly emitting electromagnetic radiation. And as it does so, it loses energy of its own. And so it should be like a planet that is slowing down, it should eventually spiral towards the middle and be stuck in the nucleus. We know that doesn't happen. So that was a problem that Rutherford's model didn't rectify. And Rutherford's model didn't have any explanation for emission and absorption spectrum. In order to explain, well, one of those for sure, and kind of get an inkling of the solution to the other one, we have to consider the Bohr model. Now, the Bohr model has for its key features electrons orbiting at only certain radii, or it would probably be better, as you'll see, to talk about these in terms of energy levels. So you can have electrons orbit in certain energy levels, and at those points they're stable. So no electromagnetic radiation is being emitted as long as they're in a stable radii or stable energy level. And the electrons only allowed certain energy transitions, so they can move from one orbital to another, one energy level to another. And when that happened, they gave off this characteristic photon of a certain energy. So when they move down from one energy level to another, so we'll give you two energy levels here, and if you have an electron that starts in the second energy level, when that electron moves down into the first energy level, it emits a photon. In order to get it up to the second energy level, you might hit it with a photon. And this is, you know, we went into this before, Bohr's idea of how emission and absorption spectrum are being produced. Now, the Bohr model still has its flaws, as anything that was developed by scientists 100 years ago. It wasn't totally insightful. For example, it could not explain why orbiting electrons did not give off electromagnetic radiation. So we still picture these things going around in the Bohr model of the atom, going around the nucleus, so they still are accelerating. So Bohr didn't really have a clean solution for that. So before we go forward, I just want to encourage you to consider that when we are going through these models of the atom, there's really a pattern that is developing, and that is you have a model for something that you don't totally understand, and in the case of something like an atom, you can never absolutely observe. We haven't been able to do that at this point. So you have this model, or what we might call a theory, of what the atom might be considered, might look like. And we stick with that until we get a problem or some key experiment that tells us that we need to revisit our model and create a new model. So we go from model to experiment to a new model. And that's kind of the pattern that you can see happening with the atomic models through the ages. You start with Dalton, you get cathode ray tubes, right? So then you have to come up with Thompson's model. Then Thompson model works fine for certain things, and then you start to observe things that the Thompson model can't explain. So you come up with a new theory, or after seeing that key experiment. So think of all the models of the atom that we have, from Dalton to Thompson to Rutherford to Bohr. And in between each of these, you have this key experiment that takes place, right? So cathode ray tubes led us to Thompson. Alpha particle scattering led us to Rutherford. Rutherford's model was great, but emission spectrum led us to the Bohr model. And now we're going to take it one step further, because although these are kind of what you study historically in chemistry in high school, and this is probably the most relevant model for high school chemistry, and this is probably what you use, and this is probably what you're picturing in your mind as a model of the atom. It's not the most current model of the atom. If we want the most current model of the atom, we have a model of the atom that actually explains, or attempts to explain, why electrons traveling in a circle do not emit electromagnetic radiation. So let me introduce you to a more modern idea around the atom, and that is the quantum model. And the quantum model has as its key features this. Instead of thinking of electrons as particles, let's remember that we can consider that electrons can be modeled as waves. So instead of being at one single point circling the nucleus, like we picture with the Bohr model, so it would be something like this, and we have our electron that's around the outside here, and we picture this single electron in one place in time going around and around this nucleus. Let's think about this thing as a wave. And so you can imagine as a wave, we have different ways that waves can set up. If you have taken physics 20 with me, you'll remember we did a little experiment in which we took a stretched string and we caused vibrations in that stretched string that set up a standing wave that looked like this. Then we could increase the frequency of our wave, and we ended up with a second standing wave that looks something like this. So the quantum model asks you to consider that each of the energy levels represents a distance around the nucleus through which we could get a standing wave. So we get a certain length for a standing wave here. If we want to get a second standing wave, one way to do that would be to increase the length of the string so that we could get both a crest and a trough on at the same time. Well, imagine that that's wrapped around here. So this might be the first one with a single standing wave here. Then you might get the n equal 2, where you get two standing waves set up around here. And then the third one's almost easiest to see in this diagram. You see you have like a crest here, and then a trough, and then a crest, and then a trough. You get these standing waves. So electron waves exist as standing waves around the nucleus. If you think about it, it's a good explanation as to, number one, why are electrons not giving off electromagnetic radiation when they're in a stable orbit? Because they're not really in an orbit. They're not a single charged particle. They exist in all these locations at one time. So it's not accelerating when it's in this stable state. Why is it that certain energy levels are allowed and you can't be in between the energy levels? It's because you can have a standing wave in certain patterns. You have to have either an entire crest or an entire trough, or you have to have two, or you have to have three. You can't have 1.5 standing waves, so you can't have anything exist in the 1.5 energy level. And so we are going to stop our survey of models of the atom here, not because this is the end of the line, but because this is where we choose to stop in Physics 30. But there are more, how shall I say, more intriguing, better models of the atom that explain other phenomenon. But we'll stop with this version of the quantum model of the atom, this idea of standing waves. So again, just want to encourage you to consider all of the models, but the biggest thing in this unit, again, is this idea that in order to get a better understanding of the atom, we've gone through this progression of theory, experiment, theory, experiment, theory, experiment, theory, experiment, etc., and it continues on to this day. So I would really encourage you to sit down and make sure you are clear in your own mind about the different, not just the models of the atom, but the key experiments that really moved us forward in developing new models.